Good evening, everyone, and welcome to the Amateur Radio General Class, session number 3. Our previous class, we mentioned that the following Sunday was to be World Amateur Radio Day. Trust that those hams in our midst were able to do some sort of activity for amateur radio. We also discussed the ARRL VE exam session. Also, we looked at the practice exams. We had quite a few questions that we answered for the class. And then we went straight into some of the technical material, such as reactance, the reactance formula for inductive circuits, as well as reactance formula for capacitive circuits. And we also did a comparison between the two formulae. We also dealt with impedance, the importance of impedance matching to amateur radio operators. And we looked at some circuits to achieve impedance matching, such as the LC network, transformer, use of the pi network, and also a length of transmission line. So this is where we are with respect to our curriculum. We are in very early days yet, and we are at the electrical principles section of the course. So just to emphasize, we do have or recommend practice exams. Even at this stage, you are now starting, we'd still recommend persons at least take a look at the practice exams, get a feel for what it looks like, and maybe even attend a couple of them. You might be quite surprised how much you already know. So our Q&A from our last class. So the first question was, I'm having difficulty connecting to Zoom with the audio on my mobile phone. So quite often when we install any app, such as Zoom, it will ask for permissions to be granted, such as the microphone, camera, contacts, file system, and so on. And that is to enable the app to function properly and automatically. But of course, you know, because we are very concerned and conscious of security, sometimes we answer no to those questions when it comes up. So you can check your security settings for Zoom to ensure that the required permission is granted to the app. You can also sometimes uninstall and reinstall to get prompted again with the questions so that you can select the answers to give permission. The next question was, I had difficulty getting onto the Zoom session, but the YouTube worked. Okay, so unfortunately, for the last session, the short link did not work for some participants. So therefore, a long link, or the long link, will be also provided going forward. So when you get your weekly email that contains the previous week's slides, as well as the date for the next session and time, you will get the short link as we have been providing before, but also we'll provide the long link should in case the short link not work for you. Right. Also, just a reminder, we're also streaming live to YouTube. So an easy way would be to just search YouTube for 9Z4RG and look at the live stream there. Also, we do make announcements, even though persons are having difficulty may not get on, because we know several of you know each other. We will make the announcements in class so that you can help your colleague out as well. So we will now go and take a look at the question pool related to the theories that we had a look at last class. So remember, we are using the No Nonsense Guide, General Class License Study Guide by KB6NU. And the URL at the bottom of your screen is the link to Amazon for the book. So many persons have also out of band asked that question. So we're providing the link here for that particular book. Just make sure that when you're purchasing the book, that you select the current question pool, which is July 2019 to June 2023. There is a book for the previous question pool. Nothing technically wrong with going with an older book, but some of the questions would have changed since then. So it makes sense to purchase the current book so that you will have all current information. So let's just switch up now to the no nonsense guide, and we will go through the question pool questions. So as indicated, we will be taking a light touch theory approach and exam focus. So we jump straight to the questions related to the theory that we looked at last class. And notice one of the reasons why I use this particular book in the teaching sessions is because the focus is on the correct answers. We leave it up to you to look at the distractors. So for instance, just a tip, on the no nonsense guide, you will see a number next to the questions, G5A02, for instance. That is the question number. And this will match up with the question in the question pool, which was also circulated to all participants after the first class. The question pool has all 500 plus questions, as well as the answers, including the distractors. So if you want to match up a question on the no nonsense guide to the question pool, this is how you do it. You look for this number that's next to the question, and you can match it to the question pool. But as said before, we will be focusing on the right answer only. Leave it up to you when you're studying to look at the distractor question answers or the wrong answers, right? You'll have an A, B, C, D, and we'll be focusing on the right or the correct answer. So based on the material we looked at last class, let's go straight into the question in the question pool. So first question we have, what is reactance? Well, we dealt with that in the slide deck last week, so I hope persons had the opportunity to review the slide deck and or the recording. And reactance is simply the opposition to flow of alternating current caused by capacitance or inductance. Remember, we had a couple of slides on reactance. So if this is not sounding familiar to you, I encourage you to look at session number 2 that goes a bit of detail into reactance. So this is the correct answer. So we'll be going very quickly through these questions because we touched on the theory associated with these questions last class. Next question in the question pool. What unit is used to measure reactance? And as we learned last class, it's the ohm, similar to resistance, if you recall from the technician class. Once we're talking reactance, we use the ohm as the measurement. Next question in the question pool. Which of the following causes opposition to the flow of alternating current in an inductor? Well, again, just another way of asking a similar question. The answer is reactance. So we're talking reactance here, so therefore reactance is the correct answer. Okay, so another question again, but just change up slightly. Which of the following causes opposition to the flow of alternating current in a capacitor? So notice the difference between the two questions, this one and the previous one. They're asking here about the capacitor, and we also had the question about an inductor. That's the only difference between the questions. But we know that the opposition to flow, whether it's a capacitor or an inductor, is reactance, okay? So let's go to the next question. How does an inductor react to alternating current? Remember, we had a slide that we did a calculation to show when one variable increased, what happened to the other variable. So we did that for both the capacitor and the inductor, or capacitive reactance and inductive reactance. So that is why we went through that to show and prove, instead of just learning by rote, when one thing increases, the other thing decreases and so on. We looked at the formula and we looked to see when we increased the value, what happened to the other value, the dependent value variable. So the answer to that question, as we discovered last class, is as the frequency of the applied alternating current increases, that is F in the formula, if you recall, the reactance, which is X, increases. So if you remember that formula, as F goes up, also X goes up. Why? Because it's directly proportional, right? And here's the formula here. There it is. In an inductor, when F is increased, X also increases. Okay, so next question. how does a capacitor react to alternating current? So again, similar to the previous question, the only difference is instead of an inductor, they're asking us about a capacitor. But remember that this is the formula. Reactance is equal to 1 over 2 pi fc. So therefore, F now is in the denominator. Therefore, when you increase frequency, what's going to happen to reactance? And as we proved in our last class, as the frequency of the applied alternating current increases, the reactance decreases. So now you're seeing why we went through all of that last class to prove when something increases, what happens to the other variable, because these are actual questions in the question pool. All right, so once we understand the formula and we understand when one value or one variable increases, the other one does something, that is what's going to help us with this. So if you need a refresher, just have a look at session number 2. Okay, we also dealt with this concept last week, that of impedance. So the question in the question pool is simply, what is impedance? And as we learned the last class, it is the opposition to the flow of current in an AC or an alternating current circuit. Yes, so let's continue. We also dealt with the concept of matching at the last class during the slide deck. So let's go straight to the question in the question pool that dealt with that. So you see how they're asking the questions, right? What happens when the impedance of an electrical load is equal to the output impedance of a power source, assuming both impedances are resistive? So let's dissect that question a little bit. It's a little bit long-winded. So let's make sure and pick out and pull out what are the critical terms there that they're asking us about. So they ask us what happens, right? But they're asking us about impedance. That's what they're asking about, impedance. And what happens when the load is equal to the source? All right, so you have a source and you have a load, and we're asking when the impedance of both the load and the source, or as we had looked at in the slide deck, the transmitter and the antenna, for instance, what happens when the impedance is equal? Yeah? And we have here, it says when it's resistive, right? So we're talking about impedance and equality between the load and the source. And we said last class, when that occurs, remember we said hams are matchmakers, that's what we're actually trying to achieve. The answer is the source can deliver maximum power to the load. That's what happens when your impedances match between the source and the load. Okay, so another similar question. We said there were different ways to match. Remember, say hams matchmakers. Okay, so we're doing that all of the time. That's what we're trying to do. Next question in the question pool. What is one reason to use an impedance matching transformer? Well, what that does, it matches the load to the source, and just like above, it ensures that we have, the answer is, to maximize the transfer of power. That's what we're trying to do. We don't want to waste power. We want to maximize. We don't want to waste any energy. So we're trying to match the impedances between the source and the load, your radio and your antenna, so that you have maximum power delivered. Next question in the question pool. Which of the following devices can be used for impedance matching at radio frequencies? So let's pause to dissect that question a little bit. So they're asking about devices. Which devices? All right, so last class we learned about some devices or some circuits. And to do what? What must these devices do? Impedance matching. So that's what we're about. What devices did we learn last class can we use, or what circuits can we use to have impedance matched? And we learned about these three circuits or devices: a transformer, the pi network, and a length of transmission line. All of those can be used, and therefore the correct answer for that question is all of the above, or all these choices are correct. Okay, last question before we switch up to the slide deck. Which of the following describes one method of impedance matching between two AC circuits? So remember, we dealt with the three above here in terms of matching, but we also dealt with something called an LC network. Those four things were on the same slide, on the slide deck. So that's the answer as well for this question, the LC network. So you insert an LC network between the two circuits. That's how you match two AC circuits, an LC network. Okay, so we are now back to the slide deck and we go into some more theory. And in a few minutes, we will take a short break. So let's go straight on in. So another theory that we need to learn about for our amateur radio exam is Kirchhoff's current law. And Kirchhoff's current law simply says that the total of the current in a circuit, the total current in a circuit must be the sum of all of the currents in the branches. So if you look here on the screen, let's pull the mouse, right. So the current that is leaving this point on the circuit is being split into two branches. So you have I, which is your current that's leaving, and it's conventional current we're talking about here, conventional flow of electricity. So the current that's leaving here gets split into two branches. Now this is a parallel circuit, as we would have learned from the technician class. Also, it's strictly a resistive circuit where you only have resistors. You see two resistors here. So the current is splitting. How I like to think of that, remember we discussed water circuit as an analogy during our technician level. Well, we can use water here as well. We can think of water leaving in this pipeline. There's no way of the water leaking out. And when that water goes along the pipeline, it goes in two directions. It goes this way and it also goes this way. And it returns back to the pump, right? So that water is circulating. So the total amount of water that leaves the pump and goes here must also be the total amount of water that comes here. So when the water splits between these two pipelines, when they recombine, the total is the sum of the water that flows in these two branches. So the same thing with current. The current that leaves the battery or the voltage source and goes on the circuit and gets splits into two, current 1 and current 2, or I1 and I2, when you recombine, it's the total of I1 and I2. So that is simply what Kirchhoff's law says. Once you have current leaving and it's branching out into different circuits, when it recombines, it's the total amount of the current, okay? And yes, that's the question in the question pool. We'll see how that is worded if we have some time a little later on in the class today. So we're going straight on into some more theory again. And alternating current values, there are some terms that we need to become comfortable with and familiar with. It's peak, peak to peak, and RMS. And RMS simply means root mean square. So we will look at that in a little bit. But let's look on the diagram. Towards the right-hand side, we have a sinusoidal wave or an alternating current. You see it going up, hits a peak, it goes down to 0, goes back down again to another peak, and then up again. So essentially, when we look at this sine wave or sinusoidal wave, this is alternating current, right? We need to identify a couple things about this wave. If you notice this tip here, the top, that's a peak. If you look at the bottom here as well, that is also another peak. So those are peaks of the wave as it goes from 0 all the way to maximum. It comes back down to 0 and it goes all the way to maximum on the negative side, and then it goes back to 0. And that's why the current is called alternating current. It goes between one direction and the other, or some will say positive and negative, right? So we need to identify certain properties. So there's the peak, and then there's the other peak, and therefore, so the peak value will be measured from the 0 point here to the peak. So that's from here to there, that's the peak. But we also have peak to peak, which is from the top here all the way to the other peak. So if you look at this line here, that is peak to peak. So we need to understand when we're talking about peak, peak is from 0 to the top. It's like a mountain. You're standing on the road here, and therefore for the peak is the top of the hill. But then on the other side, you have the sea and you have a trough in the ocean. You know, you go down and it's deep, and that's another kind of peak. And if you look at the bottom of that trough in the ocean to the top of the hill, that is peak to peak. So the peak value is the highest value of the voltage, right? So the highest value, that's your peak. Notice it goes up, peaks, and then it goes down to 0. So peak is that highest value. And peak to peak is the difference between the highest value here and the lowest value, or the other peak, if you want to call it that, right? So from this point to this point on the diagram, that's peak to peak, but we measure it, of course, vertical distance, right? That's peak to peak. And that is, the peak to peak is twice the value of the peak voltage, right? So if you have a voltage of 5 volts, that's the peak, then the peak to peak will be twice that, which is 10 volts, 2 times 5. Okay, so we also need to get familiar with the concept of RMS, root mean square. But what is RMS? First of all, let's look at where it is on our little diagram. So notice that the RMS value of the voltage is not the peak, it's not 0, and it's not the negative peak or the lowest value here. It's somewhere above, right? So you see this red line, red dotted line, that is the RMS value. It's not the peak. The peak line would be here. So it's, and a 0 line would be here. So it's somewhere between 0 and the peak. And this is called the RMS value. Why that is significant? The RMS value is simply the value that if you had a DC circuit, it will be the DC equivalent voltage. So the amount of heat that is produced by the equivalent DC circuit, that is the voltage value, or we say the voltage that causes the same power dissipation as a DC voltage, right? So the same AC voltage that is, or the voltage that causes the same power dissipation as a DC voltage, right? So that's the RMS value of the AC circuit. So let's also talk about how we calculate the RMS value. To find out what the RMS value is, let's say my voltage is 1 volt. My peak voltage is 1 volt. If I wanted to find out what my RMS voltage is, it's a simple formula where I multiply my voltage by 0.707, all right? So as we have here, it says for an AC sinusoidal signal, the RMS value is 0.707 times the peak value. That is, to get the RMS value from the voltage on an AC voltage, you simply multiply by 0.707. That's the number, the magic number, okay? So we would come across this value in a formula in a short while. And also, if you happen to know the RMS value, which is going the other way, and you want to find out the peak voltage, you can divide by 0.707, or you can multiply by 1.414. How did we get 1.414? Well, 1.414 is the reciprocal of 0.707. If you divide 1 by 0.707, you will get 1.414. And I encourage you to try that on a calculator. Just go and punch in 1 divided by 0.707 and convince yourself that you end up with 1.414. So instead of dividing by 0.707, you could multiply by 1.414. And that is if you want to find the peak value and you have the RMS value, okay? So 2 ways to go. And if we look at the bottom right-hand side here, you will see that we have that formula represented. So we say the voltage, or VRMS, that's the RMS voltage, is equal to the peak voltage, that is what VP means, multiplied by 0.707. All that is the formula, or the way we write it out mathematically, to represent this English statement that we have here, which is to get the RMS value, we multiply the peak by 0.707. That is all that formula is telling us. So don't worry about the notation too much. The other way, of course, we said that the peak, if we want to go from the RMS to the peak, if we have the RMS, we could take the RMS value and divide it by 0.707 and get the peak. And also remember we said we could do it the other way. Instead of dividing by 0.707, we can simply multiply by 1.414. Okay, so these are the formulae that you would need to be familiar with, and we'll see that when we come back from the break. We will take a 2-minute break, and when we come back, we will do some worked examples that will hopefully clarify all that we have just said on this slide. So take a break, get a stretch, drink a water, bathroom break, and we'll join back in about the next 2 minutes or so. Okay, welcome back, everyone. So I'd just like to take the opportunity to welcome all of the new participants to the class. And also just to recognize we have quite an international audience with us as part of these sessions. And we certainly welcome everyone to the sessions. We do have a couple of questions to answer that I can deal with quickly from Amali. So Amali, thank you so much for your questions. The first one is there a particular name for the zero line? So yes, it's referred sometimes to exactly like the zero line. It can also be called the zero voltage line. It could be referred to as the horizontal zero axis. Some people might even call it the zero axis baseline. So zero line, I think, would be fine for our understanding as well. So good question indeed. The next question from Amali is the negative and positive always equal to each other in alternating current? So the answer would be yes for purely sinusoidal wave. Once it's that perfect alternating current, it should be or it ought to be. Let me just say, I mean, if you were to take an oscilloscope and look at an actual AC voltage, you might see some anomalies due to what are called harmonics. But generally, the answer is yes. In an AC, it will be equal and opposite. So very good questions indeed, Amali. So as we continue from where we left off, so I did say we'll try and make a little bit of sense of this bit of theory that we have here and the cryptic formulas that we have, or seemingly cryptic. Let's look at them. The best way to do so, of course, is to do an example. So on the right-hand side, you will see that same graph showing the AC voltage, going between positive and negative and so on, and the RMS value. So it's a little better, a little bigger on this slide, okay? But let's ask a question and let's see if we can calculate the answer that will hopefully, bring to life that formula that we learned a little earlier on the previous slide. So what if someone told us that the peak voltage is 17 volts, So we have a voltage, it's 17 volts, the peak, and we wanted to calculate the RMS value. In other words, we have an AC voltage, but we want to know what is the equivalent DC voltage from a heating standpoint or a power dissipation standpoint. What would be that DC equivalent called the RMS value, root mean square value? Well, we learned a formula earlier. That formula was the RMS voltage is equal to the peak voltage multiplied by that little magic number, 0.707. So we're going to use that formula that we learned a little while ago, and we need to commit that formula to our memory. That is our magic formula. So because the RMS voltage is what we want to find out, we are given the peak voltage. It says peak voltage is 17 volts, and we have a constant or value that we multiply by 0.707. So we just simply plug that 17 volts into the formula, and that's going to give us our next line. It says the RMS voltage is equal to 17 multiplied by 0.707. And when we plug that into our trusty calculator, we get the RMS voltage is equal to 12 volts. And you can check it for yourself on your calculator. So if we have a voltage of an AC voltage at 17 volts, notice that the RMS voltage is 12 volts, or the DC equivalent voltage will be 12. And that stands to reason. If we look at our little graph here, if this peak were to be 17 volts, the RMS value here would be 12 volts. Yeah. So that's how we use the formula. Let's take a look at another example. And just by the way, these worked examples are the actual questions in your question pool. Okay, another worked example. So we are told that the RMS voltage, VRMS, is 120 volts. Let's calculate the peak to peak value. Now, notice what we are looking to calculate, the peak to peak value, not the peak value, the peak to peak. And remember, peak to peak is from here all the way to here. Peak is just this area here, this length, this distance here. But peak to peak is all of this, from this trough or peak here to this peak here. That entire distance is the peak to peak. So let's use our trusty formula. So we learned earlier that the peak voltage is equal to the RMS voltage divided by 0.707. We also learned that another way we could represent that is say that the peak voltage is equal to the RMS voltage multiplied by 1.414, right? Remember, we had those two versions of the formula. We can simply use the division, or we could use the multiplication. But sometimes multiplication might be easier for some people. So we'll go with the multiplication. But notice that what we want is to calculate the peak to peak value, not just the peak. And we know that the peak to peak value is equal to twice times the peak value. This peak to peak is twice the peak value, yes? So that's how we have VP dash P, that's what that is in subscript. VPP, that is the peak to peak voltage, is equal to 2 multiplied by the peak voltage. Fairly straightforward, just twice times, yeah? So therefore, we plug that into our formula above, and we say that VPP, or the peak voltage, is equal to twice times VP. But what is VP? From above, we have VP is equal to VRMS times 1.414. So we just substitute, instead of VP with the peak voltage, we substitute the formula for it inside of here. So we take it and plug it in. So we end up with a formula that says that the peak voltage is equal to twice times the RMS voltage multiplied by 1.414. That's how we get all of this, yeah? And we get now, when we plug the values in, well, what are the values we plug in? Well, we have a constant 2 here, so we don't have to plug anything else instead of, we don't have to substitute. But we have VRMS. But what is VRMS? When we look here, it says the RMS voltage is 120, which is VRMS, as we know. So we put, instead of VRMS, we put 120. That is the value that we are putting into the formula. And then we have the other constant value, which is 1.414. So we just plug in 120 into that formula. And when we multiply this out, and you can try it with your calculator, 2 by 120 by 1.414 is supposed to be 339.4 volts. So for an RMS voltage of 120 volts, the peak to peak voltage is 339.4. So the RMS voltage is here, which is 120 volts. But the peak to peak voltage, when you measure that, is 339.4 volts. And this is an actual question in the exam. This is an exam question in the pool. So we have just worked it out, how you get this answer, step by step. If you need to go through it on your own time a little slowly, you can feel free to do so. All right. So let's go to another question. Oh, sorry, another bit of theory, and then we'll come back to some worked examples. So the other thing that we need to learn about, which we touched a bit in the technician class, is the concept of power, the power formula for both AC or alternating circuits and DC direct current circuits. So we're looking at power, and if you remember correctly, power is measured in watts, or the watt is the unit that we are using for power. So we say here, according to the theory, when the voltage and current are in phase, power delivered by an alternating current signal is equal to the RMS voltage times the current. So how do we calculate power? Power is equal to, okay, so I just have a little error in the formula here. This RMS should actually be subscripted, all right? So it's VRMS multiplied by I. So it's voltage multiplied by the current. Right? But RMS voltage for a AC circuit. And if we applied Ohm's law, if you remember from the technician class, E is equal to IR, or V is equal to IR. If we substitute the Ohm's law formula into this formula, we can get either P, which is power, is equal to V squared over R, or the RMS voltage squared over R, or another way to look at it is P is equal to I squared multiplied by R, or RMS, the RMS current squared multiplied by R. That's all this notation means. So let's just talk about squaring. So squaring is just simply taking a number and multiplying it by itself. So anytime you see a notation like this, V squared, that means whatever we put into this variable here, whatever value we plug in, when we say square it, all we mean is to multiply it by itself. So if V would be, let's say 3, if V were 3, V squared will be 3 multiplied by 3, which is 9. So that notation, V squared, just simply means multiply by itself. Don't get confused by this little RMS subscript. It just simply means this is voltage, but it's the RMS voltage we are looking at. Because there are several voltages that we talk about. We are looking here at RMS voltage. There could be peak voltage, there could be peak to peak voltage, and so on. So don't let the little notation confuse it. It should actually help you when you're talking about voltage to know what voltage are we talking about. And we know that it's the RMS voltage here that we're talking about. So coming back down, the power is equal to the RMS voltage times the current. But from before, Ohm's law, voltage is equal to current times resistance. So we plug that in, we substitute this into the formula, and we get power is equal to the square of the voltage over the resistance. And we also have another corollary, which is P is equal to the square of the current multiplied by the resistance. And also you need to know as well, for DC circuits, notice there's a very similar form. The only difference here is instead of saying VRMS, we just have V. And instead of saying IRMS, the root mean squared value, it's just regular I. Okay, so that's the difference between the DC formula here. So remember, this is the AC formula for when the voltage and current are in phase. All right, we'll learn probably later on, what that means when they're out of phase. But for now, we take it for granted that the voltage and current are in phase, and these are the formulae that we use. Let's go to some worked examples that will help us understand this bit of formulae that we just went through. Okay, so I'm seeing quite a few questions. So we will deal with those questions hopefully in the Q&A section, right? So again, I do apologize for new students. We try to answer questions during this session, but just to keep to the 1 hour time, we will defer some of those questions to the Q&A for the next class. So let's go straight into a worked example with the power formula. So we just presented power formula for both DC and AC. So let's look at an example here with DC, the DC power formula. And I'm just putting circuits to the side so that we can have an appreciation for the type of circuit that we're working out the problem to, all right? You don't have to worry or learn this, but this may aid some of us in understanding the material when we see what the circuit is going to be like or could look like that we're working out the answer to. So straight on into the question. The question is, if the voltage is 400 volts DC, and that's what VDC means. It's 400 volts direct current. So we represent it like that. The voltage is 400 volts DC. If it were 400 volts AC, we would see 400 VAC. All right. So you're getting a little bit into the jargon of how we represent values and so on. So this is 400 volts DC. And is supplied to an 800 ohm load. How many watts of electrical power are used, right? So that should be how. How many watts of electrical power? So it's asking us to calculate power, yes? But it's asking us to calculate power given the voltage and given the load or the resistance. So we know that the formula for power when we have the variable voltage and resistance is P is equal to V squared over R. Remember that from the previous slide? P is equal to V squared over R. Here it is. P is equal to V squared over R. That's the formula that we're using. So we plug the values into the formula. So P is equal to V squared over R. What is V? They gave us V in the question. 400, so V is 400. What is R? Well, they told us it's 800 ohms load, so that's R, 800. So we plug that into the formula, but notice we have to square V. We have to multiply V by itself. So it's 400 squared. Yes? All right, so this is repeated here. So we just go straight down to 400 squared is 160,000 divided by 800, which is approximately 200 watts. Okay, so this is an application of the power formula when they give us the voltage and the resistance or the load. We can plug it in and determine what the power used is. All right, so that's how we apply that formula that we looked at earlier. Let's look at another worked example. And by the way, all of these examples are actually from questions in the question pool. So when you see an answer, you'll be able to come back to the slides and look at how that answer was obtained. Okay, here's another example. Again, we are still with DC power, direct current. It's telling us if a 12-volt DC light bulb draws a current of 0.2 amperes, how many watts of electrical power are used? So again, they're asking us to calculate power, but this time instead, they are telling us that we have the voltage, or we know the voltage, and we know the current. So we therefore need a formula that has voltage and current that we know so that we could work out the power. And that formula, again, from the previous slides, if you look at it here, notice we said P is equal to V multiplied by I. That is our formula. Well, we simply use that formula and plug the values that are given. They have given us the answer literally. They have told us it's 12 volts and they have told us it's 0.2 amperes, voltage and current respectively. So we take the 12 and plug it into V. And we take the 0.2 and we plug it in to I. Okay, so therefore we get from that P is equal to 12 multiplied by 0.2 or 0.2. When we multiply that out, we get P is equal to 2.4 watts. So that's the application of the formula. Fairly straightforward. It might have looked a little cryptic when we went through it, but this is applying the formula to solve a problem. And this diagram here is an example. It talked about a voltage source and a bulb, a light bulb. So just to kind of keep it real, so we're not talking about things in abstract. This is what the diagram or the circuit diagram may look like for this type of circuit that the problem is referring to. Let's look at another power problem. All right. So we can also be asked to calculate power dissipation or power used by someone telling us what the current is and what the resistance is. All right. So let's go. If a current of 7 milliamperes flows through a 1,250 ohm resistance, how many watts are dissipated? And we know if we were to dissect this question, they say how many watts, but we know watts or watt is the unit of power. So they're asking us, what is the power that is dissipated? So we know that we need to find a formula or use a formula for power equals something, right? But what did they give us? They give us the current, 7 milliamperes. That's current, right? And they give us the resistance, 1,250 ohms. So therefore, we need a formula that tells us power is equal to something with current and something with resistance. And if we were to go back to our slide again, here we have it, right? We have that power is equal to I squared multiplied by R. Okay, so let's use this formula. Okay. And this is the circuit we're dealing with here as well. Okay. So we use that formula, P is equal to I squared multiplied by R, or the RMS value of the I, of the current, right? So don't get confused with the extra letters. It just simply means the RMS value of the current. P is equal to I squared multiplied by R. What is I? I is given as 7 milliamperes, right? Not 7 amperes, 7 milliamperes. So we need to bear that in mind. And we have to square it. And what does squaring it means? It needs to be multiplied by itself. So, of course, I have a little error here as well. This should be 0.072 squared. So sorry about that. But when we square 0.072, we get 0.000049. Okay, so again, we're simply plugging in 7 milliamperes into the I. But because it's milli, we need to divide by 1,000. That's how we end up with that value. So again, apologies for the slight error that we have there as well. Right, I have some typos on the slide. I'll try to correct them for the next section, but let's just go with it, right? The idea is we multiply out the values and then we end up with power is equal to 61 milliwatts. So this is basically the flow, how we get the calculation. I will fix the typos on this slide for our next class. Yet again, let's do one more example. Again, on what? Power. So here's another way they can ask you a question about power. They can ask you about power when they give you the voltage and the resistance. So the question is, what would be the RMS voltage when a 50 ohm dummy load is dissipating 1200 watts? Okay, so what they are actually asking you here, they're not giving you the voltage, they're asking you what that voltage would be if you have a 50 ohm load that dissipates 1200 watts of power. So they're asking you, given the power and given the resistance of the load, what is the RMS voltage? So we have to use that same formula that has these three terms in it, but we will have to do some moving around of the formula and put it into a form that we can get the value that we want. So what did they give us? They gave us the power, that's P. They gave us the load or the resistance, that's R. And we want to find out the voltage. So we use this formula, P is equal to V squared over R. Now, because we want to solve for V squared, we do some algebraic manipulation and we bring it such that the term V squared comes in front and is equal to something. So we simply move it around and we end up with V squared is equal to P multiplied by R. I think in the no-nonsense guide, they have an error as well, a typo. I think they have P over R or P slash R. So I believe they have made a little errors as well. If you're following along with the book, I think there's a typo there as well. We all do make some errors from time to time, okay? So V squared is equal to P multiplied by R. So we know what P is. They have told us that P is equal to 1200 watts, that's the power. They have also told us that R is equal to 50 ohms. So let's just plug it into the formula. That's what we do here. We plug 1200 in where P was, and we plugged 50 in where R was. So we get V squared is equal to 1200 multiplied by 50. When you use a trusty calculator, you do it mentally, you'll see that that is 60,000. So V squared is equal to 60,000. But we don't want V squared. We want, they ask us, what is the RMS voltage? We don't want the square of the RMS voltage. So if we have the V squared is equal to 60,000, how do we then get what V is equal to? Well, the opposite of square is square root, right? So if we have a square on one side and we want to find out what the actual value is, we take the square root of the other side. So we say now that V is equal to the square root of 60,000, and we can use our trusty calculator and take the square root of 60,000, and that will give us 244 volts approximately. Okay. So let's go on now to another concept that we must be familiar with as amateur radio operators. And that's the concept of PEP or PEP, peak envelope power. All right. So we do have a number of questions that are coming in fast and furious in the chat, and we will deal with them in the Q&A. So thank you so much for the questions. Really appreciate them. And don't forget, you can also email questions or WhatsApp questions as well. All right. So PEP or PEP or peak envelope power, what is it? Well, it's defined as the maximum instantaneous power achieved when transmitting a phone signal. And if you remember from the technician class, a phone signal is basically when amateur radio operators use voice. That is basically what you could think of as when we say phone, meaning that we are talking, right? So when amateur radio operators are picking up a microphone and talking, we often say that is using the mode phone, right? So Don't think too much of telephone as such. It's simply using voice for now. You could think of it that way, all right? So there are two different conditions under which we need to consider the peak envelope power. But if we were to use an instrument called an oscilloscope, and sometimes having a visual representation for an abstract idea could help us understand. So we talked about a signal that is unmodulated, or a carrier that is unmodulated. So no one is speaking, and there's a carrier, and therefore it looks like this. It's constant and it's continuous and it's unmodulated. It's just the carrier itself, the frequency, but no voice or no phone signal is being applied in this case. So therefore, once you have a carrier that is unmodulated, we say that the peak envelope power is equal to the average power because it is not changing. So the average is the peak. And that is actually a question in the question pool. That's why we need to deal with this. So if you see for yourself, it's just staying there, and therefore the average becomes the peak. So it's a 1-to-1 ratio, and you'll see those sorts of type questions in the question pool. But this is how you think of it. It's an unmodulated carrier. So you have a constant signal that's going, and therefore the average is the same as the peak. Now that is different to when we're using single sideband transmission, where when we speak, it changes the carrier. You see there's modulation being applied, and therefore the average is no longer the peak. The average actually, because the amplitude is varying with time, the average may be different. It may be less, and they say it may be considerably less. So notice the one above here, the average is the same as the peak, yes? And the second graph here, you can see that it's going down and coming up. So therefore the average cannot be the same as the peak. It's actually going to be less. And those are actual questions in the question pool. They will ask you that for an SSB signal, what is it the 1-to-1? Is it less? They will ask you also for an unmodulated carrier such as this one, is the average the same as the peak, or what is the ratio? And you would need to know that is 1-to-1. So that's why we have these up on the slide deck. So let's do a work example with respect to peak envelope power using some of the formulae or formulas that we dealt with a bit earlier. Okay, so let's see if we could wrap up the session with this last work example. So the question is, what is the output PEP or peak envelope power from a transmitter if an oscilloscope measures 500 volts peak to peak across a 50 ohm resistive load connected to the transmitter output? So that looks like a pretty cryptic question. So let us dissect it. What are they asking us to calculate? They are asking us to calculate PEP, which is peak envelope power. So at the end of the day, when we calculate something, we need the answer as power, and power is given in watts. So we know the destination. We want to go for power. We need to calculate power. So we need to use a formula, or maybe more than one formula, to end up with power. But what have they given us? So we want to find out power is equal to something. But what have they given us? They have given us the peak-to-peak voltage of 500 volts. They have also given us the load, which is 50 ohms. All right? So therefore, we need to apply the appropriate formula to ensure that we end up with power is equal to something. So we have to do so in a bit of an indirect way here. So if you recall from before, we had the formula where voltage is equal, or the RMS voltage is equal to the peak voltage multiplied by the magic number, 0.707. And in the Q&A section next week, we'll explain why I'm calling it the magic number. That's just a term I choose to use. But there's a way to get that 0.707. For your purpose, you just need to know this number. But we'll discuss it in the Q&A a bit, given that there's interest. But notice that the peak voltage is actually the peak to peak divided by 2. So they gave us the peak to peak. So we need to work out what the peak is, right? So that's why we have to use this other formula as well to show that peak is equal to the peak to peak divided by 2. And when we plug this formula into the one above, we end up with the RMS voltage is equal to the peak to peak divided by 2 multiplied by 0.707. All I did here was replaced the VP with the formula for VP, right? So this formula here is actually this here. So this here has been substituted into VP because it's the same thing. So I've just plugged that in and expanded the formula a little bit so that we can show how we plug the values into a formula to get a value. So because the peak to peak voltage is 500, we plug it in here. That's what VPP is. And we have divided by 2 because we want to actually get the peak voltage. And then we simply multiply by 707, and that gives us the RMS value. We work it out. Half of 500 is 250, multiplied by 0.707. If you use your calculator, trusty calculator, you'll get 176.75 volts. So we now have the RMS value. We also have the resistance, which is 50 ohms. So we need to use the formula that says power is equal to the RMS voltage divided by the resistance. This is where this formula comes in. So we have the R, which is 50 ohms here, which will be in the denominator. And we also have VRMS. What is VRMS? Well, we worked it out here. We said VRMS is equal to 176.75 volts. So we simply plug that into the formula, but notice that it is VRMS squared. Okay, so we have to square the value. So when we plug 176.5 into the formula, we get P is equal to 176.75 squared. And what did we say squaring was? It means multiplying the number by itself. It's a big number, so we use a calculator. Therefore, we get P is equal to 31,240.5625. That's what it works out to. And we divide it by 50. When we divide that by 50, we get 625 watts. Again, there's a little duplication here. Apologies for that. So P is equal to 625 watts approximately. So that is how we get this answer. When you'll go through the question pool, you will see a question that looks exactly like this, and you'll see answers including 625. This is how we apply our formula, and this is how we end up with our answer of 625 watts. So we have come to the end of today's session. We're not too bad on time. It's 9:35 p.m. Eastern Daylight Savings or Atlantic Standard Time. I'd like to thank each and every one of you for being a great class, really good questions that we have coming in, very good interests as well. We ask persons who have not yet done so to continue, please, reviewing the technician class material. You will see what we are doing in the general class builds on the technician class. So if some of these things are looking a little bit, you need refreshers and so on, looking a little bit odd, please do take a look at the technician class videos that's available at tech.ttreact.com. 16 sessions there, 1-hour sessions. Please look at them, especially for the new persons who have just joined the class. This is a prerequisite that you go through. They're all up on YouTube and you can view them at your leisure. Please be safe out there. We have a rise in COVID-19 cases in TNT. Take good care of yourselves. We still have the La Soufrière volcano eruption going on in St. Vincent. And of course, please do assist in any which way you can. Persons who are up on Zello, the React members channel, that's React space members, quite a lot of traffic. Just to advise, we'll soon be moving to the backup channel on Zello. It's also called React members, but there's no space between React and members. If you notice, there's React space members here. You can also add that channel, which is React members without the space, in preparation for switching to the new primary channel. Our next session will be next week, Friday, God's willing, Friday, the 30th of April, 2021 at 8:30 p.m. Atlantic Standard, Eastern Daylight Saving. Thank you so much, everyone. Really do appreciate it. Have a great weekend and take good care. Thanks a lot, Jeffrey. Really appreciate it as well. Thanks, Marissa. Thanks, Mark. Okay, Adish, thank you. All the best. Anthony, thanks so much. Amali, you as well. Franz, thanks a lot. Really do appreciate your presence and your encouragement. Means a lot. Hey, Desi, you too have a good night. All the best. Chevron, you're welcome. All the best. Yeah, George, give you a buzz tomorrow. You too. Pamela, you as well. Have a great weekend. Stefan, okay, great to have you there, man. You're welcome. All the best. Eustace, good night as well. Hey, Charlene, all the best. Have a good night. As well, Ramzan, take good care, man. All the best. Yeah. Jerome, hey, what's up, man? Lovely. Yeah, well, feel free to chime in too when you're ready. And Kivan, good night, man. Sylvester, hey, congrats again on your exam, successful indeed, and your call sign, well done. Ron, great to have you, man. So pleasure indeed. And June, oh yes, see you got through there, so great, wonderful, wonderful. Thank you so much. Marissa, thanks as well. You're welcome.